univariate drift detection methods that are available at NannyML, and we have quite a lot of them. And we're going to start with a theoretical section, and then we'll go to a practical tutorial. What's on the agenda specifically? First, I'm going to do a quick overview of how you should monitor your ML models. So basically, what is the flow? Why is it important? What is the flow? And what is the role of univariate drift detection models methods in that flow? Then we're going to go through the 6 univariate drift detection methods we can use with NannyML to detect drift. And then we're going to have a tutorial when we basically look how they stack against each other in practice. So starting with the monitoring flow. Why should you monitor your machine learning models? What are the goals of the ML monitoring? So the first most important goal is to maintain the business impact of the model. When you develop your models and you try to improve the performance, what you're actually doing is you're trying to maximize the business impact of the model. Whatever your model is, whether it's credit scoring, whether it's cross-sell model, whether it's some kind of NLP model for, I don't know, document classification, what you're trying to do is basically have some kind of business impact in your organization. And the proxy for that is your technical metrics. So you want to maintain the business impact of the model and the technical metric that you use as a proxy for that. The second goal is to reduce risk of the model, because the models work with real life data that's changing and it's not fully predictable. And there's always a chance that the model will fail, and machine learning model failure tends to be silent in a way that the model will still make the predictions, but the predictions will no longer be correct or as correct as they used to be. So by knowing what's going on and having full observability of your system, you are reducing the risk of that model. And then the third goal, more from kind of a social perspective, is increasing the visibility of the model. You as a data scientist, and maybe you as a head of data science, want to make sure that your work is recognized organization-wide, because then that can lead to promotions, it can lead to better budgets, bigger budgets, increases in the team size, and basically just furthering your career goals. So these are the goals. Now you know why you should do it. Now let's go about figure out how we can do it. So what's the process? Performance ML monitoring should always start with performance monitoring, because again, the first and most important goal is to protect the business impact. And to protect the business impact means know what the business impact is, or what the proxy for the business impact is, which is a technical metric such as F1 or MAE. So first thing, we need to know what is the performance. If we can calculate our performance, that's great. In a lot of cases, we cannot. In that case, we'll have to estimate the performance, which you could also do with algorithms that you have available at NannyML. Once you figure out that there is something wrong going on or something unusual going on with your performance, you should be able to figure out what is the root cause, what actually caused that drop in performance or the change in performance. And for that, we go into root cause analysis. And this is where univariate drift detection comes into picture. And univariate drift detection should be used as a kind of a troubleshooting tool that allows you to figure out what went wrong, and not as a way to directly monitor your models, because models with, I don't know, 50, 100 features will constantly drift. There is going to be always a feature that's drifting, and you will just drown in alerts in false positives, which will basically reduce the effectiveness of your monitoring to zero if you use univariate drift detection for monitoring and not for root cause analysis or not for troubleshooting. So that's where univariate drift detection resides. And once we figure out what went wrong, we can then go to the third step, which is the issue resolution, and basically use your domain knowledge and use the tools you have at your disposal as a data scientist to resolve the issue by retraining your model, by getting more data, retraining your model, by redeveloping your model, by changing the downstream business processes, whatever you need to do to make sure that the business value of the model is protected. So now we know that we're going to focus on the root cause analysis. Let's then look at how exactly root cause analysis can be performed. So the first thing is running drift detection methods and determine what features are drifted. So we're going to use here univariate drift detection methods. You could also use multivariate drift detection methods to do that. Then we want to reduce the false positive rate further. So first way of doing that was looking at performance, not at the drift. Second one is we're going to correlate these drift features with performance, and we're going to focus on the ones that have high correlation with the drifted feature, with performance. So we are really trying to find something that's potentially causal. Of course, this is just correlation. There's no causality there, but there is a significant chance that if these things actually change together, then features might actually be impacting performance and not the other way around. And then we'll have to use our domain knowledge in whatever industry you work in to figure out what is the actual root cause based on what you're seeing when it comes to change in feature distribution. So that's it basically. And now univariate detection. What does it actually do? So the first thing it does, it captures the change in distribution of a single feature. We can run it on all features and see how the distribution of every single feature is changing. There's a few things that it cannot do. The first one is it cannot detect changes in correlations between features and relationship between features. This is something that we can do with multivariate drift detection, which we're not focusing on today. But if it's something that you are also concerned with, especially if you have models that are nonlinear and can capture nonlinear relationships between features, such as XGBoost and gradient boosting models, or basically any models that are currently used, you should also look at multivariate drift detection. And as I already mentioned, univariate drift detection can suffer from high false positive rate. So first, we need to focus on monitoring performance to reduce this false positive rate. And then once we look at all the drifts, we should only focus on the drifts that correlate with performance to further reduce this false positive rate. So that's basically it. Now we're going to go into the second part of our presentation when I'm going to talk about every single univariate drift detection method we have at our disposal at NannyML. And we're going to go through three things. But first, click at a glance comparison. We have 6 methods here. 4 of them can be used for categorical variables, which is the Johnson-Shannon distance, Hellinger and distance, L-infinity distance, and chi-squared test. And there's also 4 that can be used for continuous features. So again, Johnson-Shannon, Hellinger again, Wasserstein distance, and Kolmogorov-Smirnov test statistic. And then most of them will be in the range 0 to 1, which makes the interpretation quite easy, except the 2 that go all the way to infinity, which makes the interpretation potentially a bit harder. So now we're going to go through all of those. And the way I decided to structure it is that we're going to have 3 slides for each of the metrics. The first one will just cover the basic, what the method is, how does it look like? Again, what is the range? What is the thing that it works on? Just a quick reminder of the at a glance comparison you saw. Then we're going to try to build some kind of intuition about how the method works. What does it try to represent? What does it try to capture? And then the last thing is that I run all of these methods on a example data sets, and then I just put output of that, so you will see how similar or dissimilar the results are for a given feature in a given data set. And then we'll also learn how to read these results fully and see what are all the nuances there that we can potentially find. So without further ado, let's get rolling. The first one is the Johnson-Shannon distance. And let's cover the basics. So again, it covers both the continuous and the categorical features. When it comes to the quick intuition, it is based on KL divergence, which is probably one of the best known ways to kind of compute the divergence, the difference between 2 features. I'm trying to not use the word distance because KL divergence is actually not a distance measure. But Johnson-Shannon distance, which is based on KL divergence, is a distance measure. If you're familiar with KL divergence, you can already potentially start building intuition how Johnson-Shannon looks like. And it's based in the range 0 to 1, where 0 means that there is no drift whatsoever, and 1 means that the distributions are completely different. So the reference distribution that we will try to compare our new distributions to is completely different than the new distribution. Now, the intuition. So what we're going to look at here is that there's going to be a reference distribution for which we know everything is fine. And then we're going to look at the analysis distribution which is the distribution equation for which, let's say, the performance has dropped. And we're gonna try to see how these distributions are different and how they actually look like. So here you have examples of basically how it can look for both continuous and categorical data. Starting with the continuous data, continuous features, what it does, it captures the amount of overlap or the amount of lack of overlap, to be a bit more precise here, between two distributions. And it works kind of as a bidirectional K divergence. So as you potentially know, KAL divergence is asymmetric. So if you compare distribution A to distribution B, and then you compare distribution B to distribution A, you might get a different number. Jensen-Shannon distance is symmetrical, and basically what you see here is in red, as you will always see in red, is a kind of physical or graphical representation of the divergence or the distance measure that we're looking at. So here you see basically if these methods, if the distributions are not the same, it's gonna go higher, and it is kind of the average of comparing A to B and B to A. So you see here, they are exactly the same. It goes to 0. Here they are vastly different from each other because the analysis distribution almost doesn't exist, and the reference distribution is quite dense. So it's going to be, the divergence measure is going to be quite high. And the same here, except in categorical features, we have even nicer and more direct way of quantifying what it actually is. And it is the average of all changes in the relative frequencies of categories. So what we're looking here are the relative frequencies of categories. And we are looking at the average of all changes between A and B, B and C, etc. And what we see is basically we take the average of that, and that is our divergence measure, which then, if I remember correctly, we take the square root of to get the distance. And now results. Results will always look quite similar. So let me just walk you through how to read the graph once, and then we're going to read it the same way for every other method. So what we see on the left is our reference period, for which we would not expect any strong drifts. And if we actually observe some kind of drifts here, then we should be a bit worried if we see the same kind of drift magnitude in our analysis period, because it might be a false positive. So what you see here is basically on the x-axis is the time progression. Let's say that we trained our model on data from up to November. Then we deployed we tested our model on the data from the first half of December. And then we deployed our model afterwards. And then you see that for reference data, everything is roughly fine. There was a bit of drift in the middle. And then you see the results per chunk, so per group of observations that compare the entire reference data set at once to the value of the chunk. And that's why you can see that even in reference, this distance can go slightly higher. And if it goes above the threshold, and in that case, the default threshold is just 0.1, it's something that we empirically determined to be quite a robust threshold. And if things go above that, then you should at least take a look at them. You can, of course, change this threshold to anything you want, and you can base this threshold on two things. You can either set a constant threshold, such as 0.1, or you can base it on the standard deviation or variance of the measure in the reference data. And in that way, you can basically make kind of a dynamic threshold that's going to change based on your reference data. And here we see that the metric increases at some point. We have then alerts, which tell us something's off. It's a separate column in your results that you can then later use to potentially do some kind of automated retraining, automated checks based on whether you have alerts on your univariate drift detection measure. So that's it. Now we're moving to the second one, which is the Hellinger distance. And again, it covers both continuous and categorical data. It is similar to Bhattacharya coefficient. I hope I pronounced it correctly. And the way it's similar is basically it's just a mathematical function where the square of Hellinger distance is 2 times 1 minus the Bhattacharya coefficient between two distributions. But the reason I mentioned is that the Bhattacharya coefficient is also quite popular as a distance measure, as a divergence measure between two distributions. But again, it is not a distance in a sense that it does not fulfill the triangle inequality. So we decided to implement Hellinger distance instead, because it fulfills triangle inequality, which makes it slightly easier to interpret and work with. And just like Jensen-Shannon distance, it is in 0 to 1 range, and again, 0 is no drift, 1 is significant drift. And the intuition is quite similar again, and I promise you all the others will have completely different intuitions, so bear with me here. And here, what it actually quantifies is the overlap between the probabilities assigned to the same event by two distributions. So let's say you have an event, and the event is the value is going to be 4. And then it's going to look at this event and it's going to quantify the overlap between the reference distribution and the analysis distribution. And here we see that the overlap is almost non-existent. And as the overlap increases, then the measure is going to increase, which is here we see in the Hellinger, if I remember correctly, divergence, or part of the formula is just the integral of the square root of one multiplied by the other, which is literally just overlap between the probabilities. And similarly, in terms of categorical features, you basically take the overlap or lack of overlap here, and you look at the distance, and this distance then is used to calculate the Hellinger distance. It has one potential problem, which is it does not differentiate between very strong shifts. So imagine that your distributions are already really far apart from each other and there is no common support. So there's no overlap. If there's no overlap, then the Hellinger distance is going to be 1. If you move them even further apart, the Hellinger distance is still going to be 1. So that is a potential drawback, but of course in practice that rarely happens. And as you probably already see, it's qualitatively similar to Jensen-Shannon, whereas Jensen-Shannon is slightly more robust to changes. And results, as you can see, again, very similar, except here it doesn't go that high up in reference, but it's not something to really read into. The readings here are really, really similar. Now we go to our third measure, which is the Wasserstein distance. And here it only supports the continuous features. When it comes to the intuition or the analogy, it has a few other names such as earth mover distance, and I will describe shortly why it can be called earth mover distance, because it has a very nice physical interpretation. And unfortunately, it's in the range 0 to plus infinity, so you cannot that easily quantify how strong the drift actually is. So now, going to the intuition. It has beautiful physical interpretation, which is the Hellinger distance is just the amount of work needed to transform one distribution into the other. So imagine that the distributions are like piles of dirt, and you have one pile of dirt, which is the reference, probability density function, and you have the analysis probability density function. And if you were to transform one pile of dirt into the other, and you would calculate the amount of work, which is actual physical, physical equation for the work, and it would give you the Wasserstein distance between two distributions. And the way it's calculated mathematically, it's the area between the cumulative distribution functions. So CDFs that you see here. Quick reminder, PDFs, so probability density function, just give you the density of probability function. So how likely is a given value to fall between any two of the starting point and the end point, and the cumulative distribution function is how likely it is for a value to be at or below a certain point. And here the shaded area is literally just the Wasserstein distance, so it's one of the easiest one to understand. And Since I mentioned that it is the amount of work needed to transform one distribution to the other, imagine that you have piles that are almost on top of each other, or distributions that are almost on top of each other, except one of the distributions has a small pile of dirt, small outlier, very far away. It would still take a considerable amount of work to transform one into the other, just because there is some outlier really far away. And that means that this distance measure is sensitive to outliers, which might be a good thing if you care about outliers and you want to basically capture all of them. But of course, it can increase the amount of false positives if outliers happen in your data and they're quite normal. So something to bear in mind when you choose which measure to use. And the result here, you see that we don't have outliers in our trip distance feature. And there's only one place when we have an alert, something to look into, and we'll go deeper into the results later on. Now, our fourth feature and the last one that supports continuous data types is the Kolmogorov-Smirnov test. And important thing here, it's a statistical measure. It's not a distance, which means that you cannot do all the nice things that you can do with mathematical distances. But it provides you with the statistic and the actual p-value, which might be useful to determine the significance, at least from statistical perspective. And the intuition is, again, extremely simple. Where here, instead of the shaded area between those two, it's just the maximum distance of the cumulative distribution functions. So here, we just look at where they differ the most in terms of CDFs, and we just take the maximum of that. That means that it's not so sensitive to outliers, of course. It also means that if there's some kind of weird changes in the data where your maximum distance between CDFs stays the same, but the functions still change, KS test is going to be blind to that. It's not going to be able to capture that kind of change. And as most statistical tests, if you basically determine the significance or the alerts by the p-value, it's going to be very prone to false positives, especially in bigger samples. If your sample size is, let's say, 500, which is normal for a chunk, let's say you do monitoring weekly, or you do monitoring daily, or even hourly, it's quite likely that you will have 500 or more samples in your data. You will almost always get statistically significant change, but that does not mean that this change is significant from the monitoring perspective. So that's why it's potentially prone to false positives, but we have a way to ways to work with that. And it outputs both our D statistic, so our kind of a divergence statistic, and the p-value, which you can use then to determine statistical significance. And the results here, as I mentioned, we don't have to rely on p-values to determine the alerts. We can still just have a threshold. And here, instead of setting up the threshold that's based on specific number, we can also, as I mentioned, set it on the standard deviation value, and the default threshold for KS test is the actual pre-standard deviations of the test statistic on the reference data. And you see here that we only have one alert, so we kind of get rid of a lot of false positives. And I'll show you later on what happens if we instead decide to go with p-values. And that's what I'm going to show you, how to basically work with p-values. So we have another statistical test. This time it's the chi-square test, which works only with categorical data. And again, it's a statistical measure, not a distance. Unfortunately, to make things a bit harder for us, it is also in the range 0 to plus infinity. So we cannot that easily determine how strong the drift actually is. And as you will see in case of chi-squared, it is actually much harder than in case of Wasserstein distance even. So the intuition, the test statistic is a bit more complex than the KS test, but what it does is basically it takes the weighted average in a sense, and it's really weighted average in quotes because the formula is not a weighted average, but you can try to understand as kind of a weighted average of the differences in frequencies between all of the categories. So basically this difference, and right here, we can take a weighted average, not fully, but slightly weighted average, and that's how you will get your chi-squared statistic. And the way it's implemented, and the default implementation that we decided for the time being to go with, has one interesting property, and I would say potentially a drawback, which is the sample size actually influences the statistic for the same drift in magnitude. So imagine that you have two categories where the drift is 50% moved from one category to the other. And the chi-square statistic will actually increase with the sample size. So if you have a sample size of 100 for one test, and then in your next chunk you have 1,000, and your chi-square statistic is actually going to be influenced by the sample size, which potentially can lead to very confusing results or misleading results. It is also sensitive to changes in low frequency categories because it looks at this difference in frequencies, and it outputs chi-square statistic and p-value. So basically, it unfortunately has quite a lot of drawbacks, and we generally don't recommend using it, even though it's one of the standards for drift detection categorical features. And the results here, I'm just going to show you what happens if you don't go with the thresholds on the statistic, but you go with the p-values. So here we have our reference data, and of course there's no alerts displayed on reference data, but you can see that there's quite a lot of variance when it comes to our reference data. And now if we compare every single chunk of analysis to the reference data as a whole, because the sample sizes are quite big, it's gonna actually say that the distributions are statistically different for every single chunk of our analysis data, which is obviously not true and not really relevant from us. Sorry, it's true from statistical perspective, but it is not relevant for us from ML monitoring perspective. And that's why using p-values to determine the significance of your drifts is generally not a good idea from just practical perspective. And our last distance before I go into the tutorial is the L-infinity distance. So again, it works with categorical data only. It is in some ways similar to Euclidean distance if you just increase the number of dimensions quite a lot, and it works in the range 0 to 1. It is quite a specialized measure. And what it captures, as you can see here, is basically the maximum difference between the relative frequencies. So we have relative frequency displayed here for our categories A, B, and C. And it basically just looks at the one that has the highest difference in relative frequencies, which means it's very nice and very good to use in features with many categories. Almost all other statistics actually will slightly increase as you add more categories, because there's always going to be slight changes in the category distributions, and they don't fully take into account, basically they don't normalize for the number of categories, or they don't control for the number of categories fully. It's just something that we saw in our internal experiments. However, L-infinity distance does, and it is very robust to noise in features with many categories. So if you have a feature that has, let's say, 100 or 1,000 different potential categories, you might want to use L-infinity distance. And of course, there is a drawback to that, which is it's sensitive to changes in just one category, basically because it's defined as a maximum difference, so it's going to look only at one category, which means that it's potentially also sensitive to changes in categories that just can appear and disappear. Then your L-infinity distance is going to be basically 1 because the relative frequency is 0 at some point. So if you have categories that really change strongly, they go from being present and strongly present, let's say 50%, and then disappearing next time. It's every single measure would show drift, but that one will be quite more sensitive to that. So that is the last one. And here we can see why you shouldn't use it. So I already told you why you should use it. Now looking at why you shouldn't use it, we have the same drop of location feature that we had previously. and we always saw that there's actually some kind of drift. But here, because there is not one single strong change, but a lot of changes in many different categories, L-infinity actually fails to capture that. And here we have actually a rare case for univariate detection methods of a false negative when there is actually a drift, but we cannot capture it with the L-infinity distance. And that is it. Now I'm just going to go through a quick at-a-glance comparison because we went through a lot of stuff, and we'll move on to the tutorial. So I'm going to skip the first 3 columns, and then I'll just go over the last 3 columns quickly. So we have for distance measure, which have a number of advantages. Triangle inequality. So if you see that there is we have 3 distributions, and we have, let's say, distribution A has certain distance to distribution B, and then distribution B has certain distance to distribution C, then you know that the distance between distribution A and C is not bigger than the sum of distances between A and B and C. This is not the case for KS and chi-squared tests, so that's something to keep in mind. And then when it comes to recommended use, Jensen-Shannon is the versatile measure that basically works reasonably well with almost all kinds of distributions and all kinds of drifts, and it's our default in the library. Hellinger distance is very similar to Jensen-Shannon. It works best with medium strings. It's really good at quantifying the magnitude there in a way that's understandable for humans, and basically works very well with our intuition. Both of those break or don't differentiate between very strong and extreme drifts when there is not a lot of overlap between the distributions. Wasserstein distance has a beautiful physical interpretation, which is work as basically a shift measure. And if that's relevant for your use case, you should definitely use the Wasserstein distance. Unfortunately, it's sensitive to outliers because of its definition. L-infinity works well with features with a lot of categories, but it's sensitive to changes in one category. And then our 2 statistical tests. The recommended use is that if for some reason you care about statistical significance, you should use them. Otherwise, you probably shouldn't, because of false positives. If you use the p-value as a way to indicate significance or positive prediction. KS test is also insensitive to changes in tails, because again, it was the maximum of the difference between CDS, and this maximum is rarely happening in the tails, almost never. And chi-squared has a lot of drawbacks. One of them with the default implementation is that it is actually just a function of sample size, which makes interpretation quite hard. And it goes all the way to infinity, which makes the interpretation even harder. And that is it really when it comes to the theoretical part. Now we are ready to go into a quick tutorial. So let's do that. Just a quick reminder, go to github.com/NannyML, and then we're going to have not our main repository with the actual library. By the way, please give us a star, but the example repository. So we're going to click here, then we're going to go to webinars, and then I'm going to go to the last webinar, which is the deep dive into univariate drift detection methods. And here is the notebook that you can use and you can code along. Now, I already have it loaded up. Make sure that it actually executes and there's nothing weird going on, because there's always something weird going on. And what I'm going to present here is basically we're going to build a very simple model on the taxi data set. So there's a quite well-known New York taxi data set where we're trying to predict oh my God, what are we trying to predict here? Yes, we're trying to, sorry guys, I need to look at it. Yes, we're going to try to predict the tip amount. So how much people are going to tip. And we're just going to build a very simple model. I'm going to skip all the things here because they're not very relevant. And then we're going to look at how monitoring for such a use case should work. So we're going to import all the standard libraries. We're going to build a model of LGPM. So we're going to import that. And importantly, we're importing NannyML. So we're going to load up the data now. It's available publicly somewhere stored on CloudFront. And we're not going to pick all the columns again, just to make the model building simpler. We're going to pre-process some data. We're going to drop some columns. We're going to create our partitions. We're going to change our data types. We're going to make sure that we work with hours. Things like that, everything totally normal. And there's one interesting thing is that because we're going to pretend that we're deploying the model, we're going to split our data into our train set, our test set that we're going to use for reference, and our production data. And again, we're predicting the tip amount, and then we're going to use all the features we have, except the partition, obviously. So let's do this, that. And now we're training the model. We're training LGBM regressor with nothing special there. No, feature engineering, no hyperparameter tuning, just the simplest thing we can do. And then we're going to predict it on train, test, and then we're just going to deploy the model. We're not going to even bother validating because, again, it's just an example for monitoring. And now we get to the interesting part, which is how do we need to prepare the data to work with NannyML? So, as I already mentioned quite a few times, we need two data sets. Your reference data set, for which you know everything is fine, and the default choice for that can be your test set. Or if you already deployed your use case to production and you have a certain amount of data for which you have the labels and you know everything is fine, you can also use that for your reference data set. It's actually prepared. And then we have our analysis data set. So the data set in question for which we actually want to do monitoring. So here we're going to use our test data for the reference and our entire production data set. We're assuming we haven't done any monitoring before for the analysis data set. And you can just see how the analysis data set looks like. We have the pickup location, we have the drop-off location, we have the distance, we have the vendor ID, we have the fair amount, so basically how much people paid. We have pickup time. I'm assuming this is pickup time from the time the person actually called the taxi. We have the predicted tip amount, and we have the actual realized tip amount, which we're going to use. We're going to assume that we actually have access to ground truth here, even though it's not necessarily the case. But since we're not focusing on performance estimation in this webinar, but on drift detection, we're going to assume we have the access to ground truth here. So we can just calculate realized performance, and NannyML has a performance calculator. We can do it, and basically you can also do the same thing in scikit-learn, of course. But the advantage here is that it gives you nice visualization in time per chunk, so you can use it for monitoring. It's quite well suited for monitoring purposes. And we're doing this, that, and we see that mean absolute error stays within certain range that we're quite happy with. For some reason, it actually drops. We're happy about that. Why not? It doesn't drop significantly, so there's nothing weird going on. But we see a period here that we are potentially worried about because we see almost 20%, or actually even above 20% increase in error. So it's something that potentially actually means that our machine learning model is failing. And then for the time being, unexplainably, it goes back. And when you see that kind of graph, you can already start using your domain knowledge to try to analyze what's going on. And here, since taxis are quite easy for us, we can already see that there is something going on around December 24th, which, as probably most of you know, is Christmas time. So during Christmas in New York, something is going on, and our model is basically breaking down during Christmas. And let's figure out what might actually have caused that change. So now we're going from performance monitoring to root cause analysis. So again, looking at the monitoring flow, first performance monitoring, we just did that. Then root cause analysis, we're going to go about it. And at the end, we can move to issue resolution. So univariate drift detection. What do we need to do? First, we're going to just make sure we have all the column names that we are interested in. And then we define which methods we want to use. We haven't done any kind of investigation before. We don't know which methods we want to use. We could just choose the default one, but here we want to figure out what is the best method to use. So we're just going to try them all and see what happens. So again, we have 4 methods for continuous features and 4 methods for categorical features. And of course, there's overlap. That both Jensen, Shannon, and Hellinger will work for both continuous and categorical features. And then once we define those, we're going to initiate or initialize, I think, univariate drift calculator, where we need to basically set what features do we want to run our univariate drift detection on, so you can run it on multiple features at once. What is the column that we want to define as our timestamp for basically plotting purposes and making sure that the chunks actually make sense. Which methods we want to use for drift detection on continuous features, which methods we want to use as drift detection for categorical features, and how big should our chunks be. So the periods of data, when we take all the data and we'll compare the distributions. And here we'll just use day. You can also use a number of items. So you can say for every 10,000 or for every 1,000 rows, we want to create a chunk. But it's easier to interpret if they are time-based. So here we're going with basically chunk every day, which is the easiest way to really interpret the results. We're gonna fit similar to scikit-learn. This actually takes a while. We're gonna fit our calculators on reference. What they will do then is they will take the distributions, and if data is big enough, they will automatically compute histograms behind the scenes, so that it doesn't store the entire distribution. If the data is quite small, it's going to store the entire distribution, because why not? And then we can calculate the drift. So we're going to just do the all the statistical analysis and all the distance calculations between the entire reference data set that we stored either as histogram or the actual data with every chunk in our analysis data frame. And now we're going to the second part. So we run our drift calculations, and we're going to the second part, which is the correlation. Now we want to see which features should we focus on. So we have a ranker here, where we can basically rank our features based on correlation with performance. So we're going to fit it on realized performance, and we're going to focus only on MAE. So we can do a quick filter here. When we focus only on the reference, make sure we don't have any kind of we'll always fit on reference to make sure there's no data leaks. And then for continuous methods, we're going to do it for continuous, and for categorical methods, we're going to basically just look at the ranking. So we're going to take our ranker and we're going to rank it. And we're going to rank it between the univariate results and the realized performance. And we're just going to compute the percent correlation between those two. There's one interesting thing, is that we can either decide to go with all the features, or only the features that are drifted. And here the reasoning is you might want to look at the correlation between the performance of all the features, just to see if there's anything weird going on with the features that are not drifting. But most of the time, we just want to focus on the features that are actually changing, because they will most likely be the cause of change in performance. So here we're going to focus only on the drifting features. And of course, whether a feature is drifting or not is going to depend on our method that we choose to compute the drift measure, so the distance most of the time. And let's see how it looks. So basically, for KS, there's only one feature that's drifting, which is the trip distance. And we have certain correlation here, which is quite high. We also have the p-value for our correlation, and we see that it is quite low. So we can say that this is quite high correlation and rather significant. So this is a feature to look into. For Jensen Shannon, we have some other features that are drifting. We have the drop-off location and pickup location that both strongly correlate with performance, and they are quite likely significant. And then we have pickup time, which we can already discard, even though it has drifted. Here you see an example of false positive. Pickup time is a feature that has drifted, but it doesn't really correlate with performance, or it's not strong at all. And it's also not significant at all. It's quite likely due to chance. So we can basically discard it from our further analysis. And here that we have, 6-7 features, you could technically go over all of them. If you have 100 features, you're going to be very likely if 40 or 50 of them drop off from your analysis just by looking at simple correlations. And same, just looking at Wasserstein, we see that it agrees quite well with KS test, that trip distance is a feature that's strongly drifting. And it is definitely drifting. It's definitely, sorry, it's strongly correlated, and it's definitely significant. And fair amount is something we could potentially look into, but we shouldn't, at least early on. And then Hellinger agrees with Jensen Sharon. We have the pickup location and drop-off location that are definitely drifting. For categorical, similarly, we have pickup location and drop-off location in chi-squared. And Hellinger, we already saw it because Hellinger works for both, just calculated it already there. Interestingly, L-infinity doesn't detect any correlations because, as I already mentioned, it focuses on single strong changes to a single category, and it's not something that we see here. So now we see the actual correlation results. We can now plot things. We already determined that for continuous features, drift distance is something that's potentially actually causing problems. Let's look at all the methods and see how they actually, whether they detect drift and how strong this drift detection is. And we see here that there is no drift detected for trip distance. For Hellinger, for Jensen-Shannon, there is one peak when it comes to KS and in Wasserstein. And here, because we can see that in Wasserstein, we see a alert. We don't see any alerts in Jensen-Shannon or Hellinger distance. We can conclude potentially that it's due to outliers. So it might be that drop in performance is caused in outliers in the trip distance feature. So we're already learning something about what is actually the root cause of our problem. But we saw a lot stronger correlations and a lot more alerts for the categorical features, the drop-off location specifically and the pickup location. So again, just to give you another example, why you should not use p-values, chi-squared, it just doesn't tell us shit. It's completely useless. Now for categorical locations, we're looking at the drop-off location here, so where the taxi dropped off a passenger. And here, if we look at Hellinger, we see actually that at first is very strongly correlated. The correlation was, I think, 0.8 or 0.7 with performance. And it looks in a similar way. If you pull up the performance here, it really goes up here. And in similar way, it goes up here. So probably change in the drop-off location is quite an important change. And we see similarly here, we have few false positives here because the threshold is set quite low compared to variance. So maybe we should have gone with variance-based threshold here. But just looking at it, you can already see that you should probably discard these alerts and focus on the ones that are really high. And here, L-infinity doesn't see anything, so there's no outliers, there's no strong changes. It's just some kind of consistent change across the distribution of the pickup location. Drop-off location. And when it comes to pickup location, we see a similar trend that we have strong changes here and also strong change on the 31st of December, so basically the New Year's Eve. And that is basically the end of analysis. Here from this, we can conclude that it's Christmas time. People were picked up and dropped off in different places. Normally, maybe they mostly go to work, and the model is able to handle that quite well. But now they were maybe in a different mindset. They were going to their family, their friends, and the tip amounts were different. Maybe they were higher, they were lower. That's something we can look later on into. But we see that it's because people were going to different places from different places, and that really caused a change in performance. Now, we should always come back to performance and look at issue resolution. How can we resolve this? The thing is, it's back to normal. Everything is fine. So we basically identified that our model does not handle holidays well. So that means that we should either look at how we can improve that model, look at specific features that are related to holidays, which we had none here, and that should already improve the performance of our model. Maybe we should collect more data from that kind of period so the model can capture the patterns better. And basically, that's how you would resolve this issue. So the model can continue operating as it is now, but there should be a flag for holidays, and we either adjust the model to work better with holidays, or we make sure that we do something there to maybe add some kind of human in the loop interaction during holidays, because we know we cannot rely on our model as it is during holidays. And that is really it when it comes to the tutorial. So now just a quick summary, and we're gonna have a quick QA session after that. So summary, drift detection is a troubleshooting technique. It does not replace performance monitoring. It's complementary to performance monitoring. You start with performance monitoring and then use drift detection to figure out what has gone wrong and confirm that the issues are there. Monitoring significance and statistical significance are not the same, as you already saw in a case of chi-squared and to a certain extent KS tests. And you should not rely on p-values and statistical significance to determine whether a feature has drifted and whether to send alerts. And last thing, as we saw, Jensen-Shannon is good default. It's not going to perform always best. There is always a case for other measures. Wasserstein, when you care about outliers, L-infinity one can about outliers, and otherwise Jensen-Shannon or Hellinger are good defaults. And that is really it. So now, thanks for listening. Give NannyML a try. We are fully free, fully open source on GitHub. Give us also a star. I'd always really appreciate that because it increases visibility in monitoring, and monitoring is very important.